All right, in this video, we're going to talk about the concavity of a graph. So whether or not a graph is concave up or concave down. So this here is a concave up graph. This here is a concave down graph, okay? So if you have a graph like this, it goes from concave down to concave up at some point over here. Okay, we call those points of inflection where it changes concavity. And we'll talk about that. Now, you can't always tell just by looking at a graph if it's where it exactly changes. So you do need the function for that sometimes, but we can estimate. It looks like it's going here, and then around here, it's changing to change concavity. Okay, so concave up is going to look something like this. Smiley face, and then concave down would look something like that. Now, it's really important to understand with respect to the slope. Okay, that's how we're going to look at this. Okay, so if the slope is increasing, it is a concave up graph. I cannot tell you how important it is to understand concavity with respect to the derivative and not just the original function. Is everything, as we work through this course, you're going to realize is we have functions, we have derivatives, and then we're going to have second derivatives. So we're going to derive, and then we're going to derive. And then the second half of the year, we're going to integrate and integrate. So this way is integrating, this way is the derivative. So as you can imagine, the AP, the College Board, they mostly give you this because then they can test you at the same time, maybe on the same question, part A, part B, they can test you how to derive something and then how to integrate something. So everything you do, you really want to make an effort at understanding the relationship with the first derivative, okay? Because that's very oftentimes how the context of these questions work out. So when we look at a concave up graph, if you just look at the regular function, it's increasing and decreasing. That's the first thing you need to realize. So concave up could be concave up decreasing, concave up increasing. So this is concave up decreasing, concave up increasing. And then concave down increasing, concave down decreasing. So that's with respect to the original function. If we want to talk about the slope, so this is the interesting part of this to me. So here I would say the slope is increasing. Now some of you are thinking that makes zero sense, right? Because if it's decreasing and increasing, how is the slope increasing? Well, if you look for the duration of this graph, let's say I drew a tangent line here. Like that. So I'm going to say that is a negative, and it's fairly negative, right? It's pretty steep on the negative side. Well, then let's say I drew a tangent line here. It's still negative, but it's less negative. Then I'm going to come here and I'm going to draw a tangent line there. So the slope equals 0. So we're going from very negative to less negative to 0. Now I'm going to come to the other side of it. Here, it's slightly positive. And then I'm going to draw one more here, which is very positive. So the slope, which is the derivative, is increasing. Because this is so important. This will make or break the class if you can understand this part of it, all right? Slope is increasing. Where over here, slope is decreasing. So it starts off super steep. Then it becomes less steep. Then it goes to 0. You get the idea now, right? And then it becomes slightly negative. And then it becomes very negative. So it's really important to understand in the context of the first derivative. Okay, so this would be concave down. Slope is decreasing, not negative, not negative. It's decreasing. Okay, so the slope is decreasing. All right, so that's basically what this is showing us here. A little bit better than I did it, but so it's negative, it's positive, it's more positive. So the slope is increasing. Here it's slightly positive, slightly negative. All right, so if you look at this graph here, this is concave down. So let's go through and find the derivatives here. So the first derivative would be, which they found for us below, it is x squared minus 1. And if I found the second derivative, it is 2x. Okay? So x squared minus 1, if I was to find the critical numbers, it's x equals plus or minus 1. So my max or mins would be at plus or minus 1, and then we could say that it's increasing, decreasing. So you'll look here, it's increasing to here, decreasing, increasing. That's what we use the first derivative for, okay? Now, the second derivative, you're going to kind of do the same thing. So we're going to set f double prime equal to 0. So this is the f double prime test, because it is not the second derivative test. So the f double prime test, so f double prime test, we're going to set 2x equal to 0, x equals 0. So now this talks, the second derivative talks about concavity. First derivative talks about increasing, decreasing of the graph, okay? That's sort of what happened here, and now we're going to start talking about concavity. Remember when we set a equal to 0, those were possible critical numbers, possible, or they were critical numbers, but they were possible max or mins on the graph. When we set the second derivative equal to 0, what we're finding are possible points of inflection where it changes concavity. So a point of inflection is where a graph changes concavity. And it's possible. So this is possible points of inflection. So possible point of inflection. So we would test it, okay? So I would test 0. So if I test to the, this is the second derivative. So if I test to the right, it's going to be positive. To the left, it's going to be negative. So that means to the right, so this means it's concave up, concave down. So to the right of 0, my graph is this is talking about the original function. So to the right of 0, it's concave up. To the left of 0, it's concave down. Okay, so for right now, let's just stick with first derivative, talks about increasing, decreasing of a function, possible max or mins. Second derivative talks about concavity of the original function. Okay, concave up, concave down, possible points of inflection. So let's stick to that for right now. All right, so this is the test for concavity. So please don't refer to it as the second derivative test because it's not. If you want to say f double prime test, we can do that internally in class, but there is an actual second derivative test which does not test for concavity, okay? All right, so here we go. We're going to work through the first derivative and then the second. So f prime, we're going to do, you rewrite it, so e to the negative x squared over 2, and then it's going to be times it's times the derivative of the exponent. So we're going to get negative x. So f prime is negative x times e to the negative x squared over 2. So then f double prime, we're going to have to use product rule here. So we're going to get, tough first question here. So negative x, then it's negative x e to the negative x squared over 2, and then plus e to the negative x squared over 2 times negative 1. So we get f double prime is equal to e to the negative x squared over 2, and then x squared minus 1. So I'm glad we addressed this now. As this happens often, we can always disregard this when we're doing either points of inflection or possible points or critical numbers, okay? Because we would never set this equal to 0, because it can never be, it's exponential. So we sort of just throw it out. So we get x squared minus 1 equals 0, and then x equals plus or minus 1. So I'm going to test around 1 and negative 1. So I'm doing the f double prime test here. So f double prime. So negative 1, 1. That's going to talk about the concavity. So if f double prime is positive, it's concave up. And if f double prime is negative, it's concave down. So I'm going to test into the second derivative. So I'm testing here. So obviously bigger than 1 is going to be positive. 0 is going to give me a negative. And then negative is still going to be positive, because let's say I plugged in negative 2. I'm going to get 4 minus 1 is positive 3. Okay? So this would be concave up, concave down, and concave up, which gives me points of inflection here. Point of inflection, because it changes concavity. Okay, so again, is when you do the second derivative test, you're testing for concavity on the original function. So remember, it goes f, f prime, f double prime. Now, something to think about is this connection. It needs to be made at some point. It doesn't have to happen right now, because I know this is a lot. But when we do f prime, and f prime is positive or negative, it describes this function as increasing or decreasing. Right? We spent some time there. We also define that concave up is when f double prime is greater than 0, or f prime is increasing, right? When the slope is increasing, so like negative, less negative here, 0, positive, that's concave up. So there's two contexts you can define concavity. It's very easy to define it in terms of f double prime, but so many times the AP demands that you do it in terms of f prime. So f prime is increasing. Concave down, f double prime is less than 0. That's obvious, okay? Or f prime is decreasing. So concave down would be, you know, so like it's decreasing, right? It's like that. So it's positive, less positive, 0, slightly negative, more negative. So it's decreasing. So if I come back here, so if we know f prime is positive or negative, it says something's increasing or decreasing. Think about this connection right now. If this is positive or negative, it's describing whether that's increasing or decreasing. So if f prime is positive, that's telling me that f prime is increasing, which is why it's concave up. Okay, sit on that for a minute. I cannot express to you how important that is for the duration of this class, okay? It's going to come up over and over and over and over again. If f prime is negative, so if f double prime is negative, that means f prime is decreasing. If f prime is decreasing, it's concave down. Okay, that's why we have those two definitions. Okay, all right, so let's come back to this. So we'd say concave up, negative infinity to negative 1, and then 1 to infinity, and then concave down from negative 1 to 1. Our explanation here is, look, the safe answer always, you could say that f double prime is greater than 0, and then because f prime is less than 0. You can never get that wrong. Okay, but again, you're going to see on some of these FRQs, it's going to be with respect to f prime. So if we're going to talk about f prime, you would say that f prime is increasing You wouldn't do both. Please don't do both, okay? Or you'd say f prime is decreasing, like that, okay? And then we'd say points of inflection occur at x equals -1 and x equals 1. We'd say because f double prime goes from positive to negative and negative to positive at x equals 1 and x equals -1. If you could be more specific, you could say at x equals -1, it goes from positive to negative, and then at x equals 1 from negative to positive. All right, determine points of inflection, discuss the concavity. All right, this one's a little bit better. Should have started off with this example, but whatever. So we have f prime. So we're going to get 4x cubed minus 12x squared. F double prime is 12x squared minus 24x. I'm going to set equal to 0, so 12x. We get x minus 2. So x is 0, x is 2. And then I'm just going to test. So we're going to test into the second derivative. Again, I like to use this here because it's easy just to kind of get a visual, because all we need is a sign. So if I'm at -1, we're looking at positive for the double negative. So negative, positive. So concave up would be -infinity to 0, and then 2 to infinity, because f double prime greater than 0. Concave down would be 0 to 2, because f double prime less than 0. All right, and then points of inflection would be at x equals 0 and x equals 2. We could say because f double prime goes from positive to negative and negative to positive. All right, so this is kind of what I talked about in the last video. Because it's so important to understand that if you have asymptotes, an asymptote cannot be a critical number, and an asymptote cannot be a point of inflection, but it's still a point of concern. So we still want it on our chart, because if you had a graph with asymptotes, you know, you can have a graph that's like that, and then you can have a graph that's like that. So it's concave up, concave down. But it's not a point of inflection because it's not in the, it can't be a point, right? It's an asymptote. It's not in the domain of the function, but we could still talk about it. So you still want to consider it, but they're not actual points of inflection or critical numbers. So when I look at this, the original function, we know that there's two vertical asymptotes. So x equals plus or minus 2, they are vertical asymptotes, okay? But they're still going to be important. All right, this video is dragging, so I'm going to just give you the first derivative. You would do quotient rule, and I simplified it up. So this is a case where you have to simplify. As if I'm just testing you on product rule, quotient rule, I don't really care how much you simplify. But this is a case where you're going to want to simplify because you need to set the top and or bottom equal to 0, okay? So f prime is equal to negative 10x and then that's over x squared minus 4. Okay, because hopefully you'll start to see patterns here, but you see how this is the vertical asymptote in the original function. That's going to stay through every derivative that you keep doing, because remember, it's always over bottom squared. Okay, and you're going to set that equal to 0 because you're going to want to put those values on your sign chart, but they're still not going to be points of inflection. Okay, all right, so let's do the second derivative. Again, you would do a quotient rule again. So we're looking at this, so simplified. So 3x squared plus 4, and then x squared minus 4 makes it a little easy because the top can never be equal to 0 because of the squared, and the plus, you're going to get an imaginary here, so we don't have to worry about that. So we're looking at the bottom. So f double prime equal to 0, there are none. F double prime undefined, we're looking at x equals plus or minus 2. So I'm still going to put them on my chart, okay? So we're going to do our chart. But I'm going to put them as asymptotes so I don't forget. Because it's easy to forget. You start testing, you're thinking, oh, that's a point of inflection. But it's not. So I'm going to test into the second derivative. So we're testing here. So I've got positive, negative, positive. So it's still concave up, concave down, concave up. Yes, for your own understanding, I really think you need to put this into Desmos and just look at it. Okay, so you can see the behavior of the graph, and you can see that it's, concave up, concave down, concave up. So none of these are points of inflection. So there's no points of inflection. And then we could still answer the question though. So concave up would be from negative infinity to negative 2, and then 2 to infinity. We'd say because f double prime is greater than 0, and then concave down, it would be negative 2 to 2 because f double prime is less than 0. All right, same thing. So we've got, so f prime is going to be 3/2 x minus 1 to the 1/2 times derivative of the inside, but it's just 1. And then f double prime is there is an inherent domain restriction on this question, so just something to think about. Because it is a square root question and you're cubing, so it would look something like this. So x minus 1 cubed, so that can become odd, not odd, negative or positive, and you're taking a square root here. So therefore it needs to be positive, so we need x to be greater than or equal to 1. But we'll see what happens here as we do this. And then you're going to do 1/2 times 3/2. So we're going to get 3/4 x minus 1 to the negative 1/2, and then times the derivative of the inside. So we're going to get 3 and then x minus 1 here. Okay? So the top not equal to 0, don't need to worry about that. Bottom equal to 0 is x minus 1 equal to 0, so x equals 1. So I'm going to test 1, but I'm going to sort of restrict it to here and beyond. So I'm going to check to the right of that. So if I check to the right of it, it's always going to be positive, so it's concave up. So concave up from 1 to infinity, and we would say because f double prime is greater than 0. So if you look here, I went ahead and I graphed it on Desmos. So it's right here. So if we look at the graph, again, we're restricted from 1 on. If you look at the graph, it is concave up the entire time. All right, determine points of inflection and discuss the concavity. All right, so sometimes you're going to have to do this with trig, which is a little bit of a pain, but same process. So we've got g prime of x. So you get cosine of x minus sine of x. And then g double prime. It's going to be negative sine of x minus cosine of x. So we set equal to 0. So you get negative sine of x minus cosine of x. So sine of x equals negative cosine of x. Is please make a note of this. So this happens a lot on the AP exam, where they ask you either where sine equals negative cosine equals negative sine, or just sine equals cosine. So whenever that happens, is you're looking at the 45s. If you think of your unit circle, the 45 is where you get the root 2 over 2's. It just depends on the sign of the x and the y. So that's just something to be aware of. So where are they opposite? I'm looking at the second and the fourth quadrant, right? Because first quadrant, they're both positive. Third quadrant, they're both negative. So we're looking at quadrant 2 and 4. So we're looking at 3 pi over 4, 7 pi over 4, like that. And then you're just going to test different points in between. We are being restricted from 0 to 2 pi. So 0 to 2 pi. So I went ahead and I plugged in different values. I got negative, positive, negative. So concave down is going to be 0 to 3 pi over 4, and then 7 pi over 4 to 2 pi. And then concave up, it's going to be 3 pi over 4 to 7 pi over 4, and point of inflection. All right, so we got to do point of inflection. So point of inflection, justification would be because f double prime is less than 0, because f double prime is greater than 0. And then my points of inflection would be at x equals 3 pi over 4, x equals 7 pi over 4. And we'd say because f double prime goes from positive to negative, or negative to positive. All right, so this is the actual second derivative test that I was talking about. Okay, on occasion, you're going to be asked to use this specifically. So the second derivative test is actually a test for extrema. And it basically states that if the derivative at some point equals 0, and the second derivative exists, we can determine if it's a max or a min based on concavity. So what do we mean by that? Well, let's say we knew that the derivative equals 0. So let's say it looks like this and like that. So the slope here is 0. If it's concave up, that's a minimum point, okay? If it's concave down and that this C value, it equals 0, well then that is a maximum. Okay, so it's a very specific test. Now, granted, most people would use the first derivative test, but I've seen where sometimes they write a question where you can't use that f prime test and you have to use something like this. Okay, so just be aware of it. It's not too common, much more common on the BC exam, but on the AB exam, you should know it. So let's start with f prime. So f prime would be equal to 16 minus 9x squared. So I'm just going to solve this. So we're going to get equal to 0. So 16 minus 9x squared. 9x squared is 16. So we're looking at plus or minus 4/3. And again, this is not ideal for doing this, but there are times where the way they create these questions, it makes sense to use this test, okay? So let me do the second derivative. So now we're going to do the second derivative. So f double prime is going to be equal to negative 18x. So what I'm going to do is plug in. So this has some sort of concavity to it. Okay, this graph has some sort of concavity. So if I plug in the point, so let's say 4/3, if it's positive, then it means at that point it's concave up. If it's negative, at that point it's concave down. So again, you don't have to get a value. All I need to know is if I do negative 18 times 4/3, it's equal to a negative number, so it's less than 0. So it's concave down. Is concave down is a maximum. So there's a max at x equals 4/3. f double prime of negative 4/3 is going to be positive, which is greater than 0. So it's concave up, which makes this a minimum at x equals negative 4/3.